So now that we've done the scaling, as well as making our initial guesses for molar fluxes, we can use Python to help us solve for the correct molar fluxes. We'll do this by solving an initial value problem, as well as graphing out the relationship between the mole fractions of all our components with respect to its location in the tube. So first we're going to need to import from a few libraries in Python. So first thing we'll do is import numpy. This is numpy. So numpy is going to allow us to use a few algorithms that we'll need, as well as use large multi-dimensional arrays. And that will come in handy. Next, as I said, we're going to need to solve an initial value problem. So solving an initial value problem is relating to integration. So from scipy.integrate, we will import from scipy.integrate, we will import solve IVP. So next, we know that our final mole fractions at an eta value of 1, so at the top of the tube, our final mole fractions of acetone and methanol are going to be 0. So eventually we are going to need to solve for the roots of a function that have different mole fractions of acetone and methanol. We need to solve for the roots of that function, so when those mole fractions are equal to 0. And this will be by changing our molar fluxes. So for that, we're going to need the ability to find the roots of a function. So from scipy.optimize, we will import root. So that's all we're going to need for the mathematical part of our solution. Now for the graphing, we'll need a few things. So from plotly, plotly.subplots, we'll need to import make subplots, which is going to allow us to make multiple plots next to each other. Next we're going to want to import plotly.graph objects, and this is going to allow us to do different forms of graphing. In this case, we're going to be using scatterplot. And finally, just personal preference, I prefer the background of my plots to be dark, so I'm going to be importing plotly.io, and this is just going to allow me to make changes to the default properties of our plots. So I'm going to do this. I'm going to change the default plot to have a dark background. Run that. Okay, we're good. Alright, so next I have listed all the parameters for this problem. So first we have the Stefan-Maxwell pairs, diffusivity pairs for components 1 and 2, 1 and 3, 2 and 3. So component 1 is acetone, component 2 is methanol, and component 3 is air. These are in base units of meters squared per second. Next, we have the pressure, which is 99.4 kilopascals, the temperature of 328.5 Kelvin, and the ideal gas constant, 8.314 joules per mole Kelvin. So we need the ideal gas law because that's going to be used in finding the concentration, molar concentration, which is equivalent to pressure over ideal gas constant times temperature, and that is derived from the ideal gas law because concentration is just moles per volume. So that is in moles per cubic meter. Next we have delta, which is given to be 0.24 meters. And then, as I discussed earlier, we have this variable f that we defined, and that's what we made the denominator of our differential equation. So we defined that to be the concentration times the Stefan-Maxwell diffusivity pair value over delta. And obviously, since this is dependent on Stefan-Maxwell diffusivities, it's going to change according to each separate one. So we have 3 separate f's to match that. Next, we have the initial guesses that we made for the molar fluxes, and the initial value of the mole fractions for acetone and methanol that were given. So we'll initialize those variables. So the first thing we're going to want to do is we're going to want to solve our initial value problem by using our initial guesses for molar flux. So we'll name N1 equal to N1I, which is our initial guess. Name N2 equal to N2I, our initial guess for the molar flux of acetone and methanol, respectively. And next, we're going to want to define a function that allows us to return an array of the differential equations for the 2 components, acetone and methanol. And if we define this function, we can then use the solve IVP feature that we imported to solve our initial value problem. So we're going to define a function dy, we'll call it, with the variable eta as our independent variable, and y, which is mole fractions, as another input. So we'll say our mole fraction of acetone is going to be equal to the first element of the array we feed the function. Our y2 is going to be equal to the second element of the array we feed the function, and our mole fraction of air is component 3. Since there are only 3 components, we know that all the mole fractions have to add up to 1. So our mole fraction of air is equal to 1 minus y1 minus y2. Next, we can return an array of our differential equations. So we'll do that by using numpy, p.array, and then we'll type out our 2 differential equations. So our first one for component 1 is going to be the mole fraction of acetone times the molar flux of methanol minus the mole fraction of methanol times the molar flux of acetone. I should put these in parentheses because this is all over our denominator that we created the variable for this pair of components, F12 in this case, minus the mole fraction of air times the molar flux of acetone over the variable we created, F13. And then our second element of the array is going to be for the next component. So let's type parentheses. So the molar fraction of methanol times the molar flux of acetone minus the mole fraction of acetone times the molar flux of methanol. And that is over also F12 because it's the same pair of components. However, the second part of this differential equation is a little different. So this one is the mole fraction of air, Y3, times the molar flux of methanol over its relationship, its pair. So that's going to be the array we were returning. So now that we are finished with this function, we can actually create a variable. We'll call it result, or res for result. And we'll actually solve the IVP. Solve IVP. So solve IVP, we need to give it a function. So we want to give it dy, the function we just created. We need to give it a span for the independent variable, and since we made our independent variable eta, as I discussed in the previous section, eta goes from 0 to 1. And we also need to give it our initial mole fractions. In this case, we defined them earlier for both acetone and methanol, and it was y1i and y2i. So we're going to solve this with the method of Radu. And we'll set dense output equal to true, so we can access some of the functions given through this solve IVP feature. Run that. So ran without any errors, but let's see. I want to take a look at res, so I'll just output that real quick. So the solver successfully reached the end of the integration, and we can see that there were not any issues in solving it. So this feature sol here has the solutions of our IVP at all the different eta values. So if I want to output, let's say I set at an eta value, or let's start with an eta value of 0, so that's at our initial liquid vapor interface. I should just get back our initial conditions, so that's good that I got that back. However, at an eta value of 1, so the top of our tube, as I discussed, we know that the mole fractions of both acetone and methanol should be 0 here. So let's check out that. Okay, so now we have a bit of a problem, right? So something's not right because these, we know, should both be 0. Well, if we think back, we just used initial guesses for our molar fluxes for N1 and N2. So since we just used guesses, it makes sense that we didn't get the right answer. So we didn't guess the molar fluxes right, which is essentially impossible. You can't really guess the molar fluxes. Guessing the molar fluxes just allowed us to get an initial solution. So now, since we know that these need to be 0, this is why we imported the root feature, so we can find the roots of a solution. So what we want to change here, we want to find the roots of this solution of mole fractions, or this function of mole fractions, by changing our molar fluxes. So we're going to do that by defining another function. We'll call it function f. So we want to define f, and it's going to take in an array of molar fluxes. And remember, when we define a function, we want what's inside the function to be tabbed over. So now, instead of making our molar flux of acetone and methanol equal to our initial guesses, we're just going to say this is equal to our first element in the array we feed it, and the second element in the array we feed it. So now we want to go down here. And just delete. So we still have this solved IVP here. However, we want to find the roots of it. And we know that we want the mole fractions to be 0 at an eta value of 1. So in this function f, we're going to return res.sol, which remember this shows the mole fractions at a specific eta value that we input. So we know that we want the mole fractions to be 0 at an eta value of 1, so we'll enter 1 here. Shift enter. Okay, ran without a problem. And now, so I'll call this variable zeros. Or let's delete this. I'll call this variable 0 since we're finding the zeros of this function. And we want to use that root feature that we imported. So root, we give root a function. So in this case, it's function f. And then we give root our initial guess for molar fluxes. And then it solves for the root by changing our molar fluxes. So we will say N1I for our initial guess for the molar flux of acetone, and N2I for our initial guess for the molar flux of methanol. Let's see. Okay, so this ran without a problem. Let's see, I want to check out what was actually in the solution. So let's see. So the solution converged, and we have this X, which gives an array of our molar fluxes that ended up forcing the mole fractions to be 0. So this is good, as we can see that our molar flux for acetone is 0.0017, which is equivalent, not equivalent, but it is the same order of magnitude that our initial guess was, so no alarms there. And same for methanol, 0.0031. Again, the same order of magnitude we estimated. So these are our correct molar fluxes. So we solved the IVP and we found the molar fluxes of both components, acetone and methanol, which is what we wanted to do. So what we have left to do is we're going to want to plot our solution. So we want to plot our mole fractions with respect to eta, which is where we're at in the tube. So we're going to go here. We'll make a figure. Just call it fig. And we want to make a figure that we can add subplots to. So figure.make subplots. And all the default settings for that are okay for what we're going to do. So next, we want to add a trace to the figure. So figure.add trace. So we imported graphed objects as GO. So go.scatter, since we're going to be using a scatter. Oop, actually, hold on. Let me go back a couple steps. Before we graph, we need to create our x-axis, so our independent variable. So we know that our independent variable is eta, and since we want to do a scatter plot, we're going to say variable eta plot is equal to numpy dot linspace, which just creates an array of values from my start point that I give it to my stop point that I give it. We'll use 0 and 1 since that is the domain of eta, and we'll do 51 values, as that'll go every 0.02, which is a pretty good amount. So now we have that x defined, our independent variable defined. We're going to want to define our dependent variables. So I'll just call that y since it's going to be the y-axis, yval. And yval is going to be equal to, so we created our x-axis, our independent variable from 0 to 1 at 51 intervals, and we're going to need to have a y value for each point. So our y value is going to be equal to this variable res that we made. and res.sol of, let's see, eta plot. So right now if we run this, I believe we will have an issue. Let's see. Oh, maybe not. So, let's see. I think we're going to need to define, so res is defined inside a function right now. So inside this function f, we've defined res. So now that we know our correct molar fluxes, we want to do this calculation again with the correct molar fluxes. So we can just say N1 is equal to, instead of our initial guess, we can say N1 is equal to zeros, which is my variable, dot x, which is an array of our solutions, and N1 is the molar flux of acetone, so we'll say it's the first element in the array, and N2 is equal to zeros dot x of the second element in that array. So if we want to just check out what that is, we can come up to a new block here. So zeros.x. So zeros.x will give the whole array, and that's just our two solutions. Alright, so now that we have named our correct molar fluxes, we're going to want to come back and grab this function that we created and bring it down here before we graph. So now we have res defined outside of this function f, and it's by itself down here. So let's see this. Shift enter. Right. So now we should be good to use this res.sol with eta plot, which is all the x values we defined. And now we're going to make our figure with the graphs, or with the plots. So figure equals make subplots. Make subplots. Again, the default settings are okay. And we're going to want to add a trace. So figure.add trace. Graph objects.scatter. We want our x to be equal to eta plot. Our y to be equal to the first element that we have in our array yval. So yval, the first element is 0. And since we did the first element, our first element is acetone, so we will clarify with a name. We'll call it acetone, and this will label it on our plot. So let's run this real quick, see if we have any issues. Okay. Figure has no attribute add trace. Oh, okay. So that's my bad. I believe add trace looks like that. Okay, there we go. So figure, we want to add a trace to it, a scatter plot with our x values of eta plot, which is a array of values from 0 to 1 every 0.02. Our y values as the, sorry, I got a phone call, ignore that. Our y values as the values in our array yval, the first element. And this is for acetone. So now we want to add two more. We have 3 components in this system, so we're going to want to add 2 more traces. So I'll just paste these here, and then I can change the independent variable will stay the same, eta plot. However, for methanol, it will be the second element in our array of yval. We'll change this label to methanol. And then our third element is going to be the third component of air, And this is not defined in y-val, but we know since we have three components, the mole fractions have to add up to 1. So we can do 1 minus y-val 0, which is acetone, minus y-val 1, which is methanol, and we should be okay. Alright, and here we go. So here's a plot of all our mole fractions, and I did it with respect to eta. So eta is defined as 0 to 1. It's essentially the proportion up the tube you are. We could do it with respect to delta, which is actually this 0.24 meters, the length of the tube. But for ease of use, I'm going to leave it with respect to eta here. So as we can see, this looks good, as it should, because at an eta value of 1, so at the very top of the tube, our mole fraction is 1 for air, and it is 0 for both acetone and methanol. And that's all.